All right, good morning, everyone. Let me introduce myself to kick off our session. So I'm Andrew Jordan. I'm at Chapman University, and I'll be chairing the session this morning on alternative formalisms. And I'm very pleased to introduce our first speaker, Yakir Aharonov, also from Chapman and Tel-Aviv University. Will be telling us about his approach to mini worlds, but also beyond many worlds in terms of boundary conditions and two-time formalism.
As you probably learned from our discussion on Thursday, I really don't believe in the many world, and I would like to find another way to solve the measurement problem. And that way is connected with the time-symmetric approach to quantum mechanics. In the time-symmetric approach, you assume that each quantum system at any time has two boundary conditions. One from experiment that was done in the past, and you evolve that vector that you found in the past to the present. And then another information is from an experiment that will be done in the future, and the result of that experiment you propagate back to the present, and you say the property of the particle in the present depends on two boundary conditions. We could not do that in classical physics, because in classical physics, once you have one boundary condition, it determines the future exactly. But in quantum mechanics, because of the uncertainty, if you have an ensemble of particles that all of them start in the same state, you can still divide them by a future experiment to sub-ensembles depending on the result of the future experiment, which is not determined by the past experiment because of the uncertainty. So in quantum mechanics, therefore, it's possible to define the particle by two boundary conditions, one in the past and the other in the future. And the question is now, if we consider the wave function of the whole universe, can we also discuss the possibility of two boundary conditions for the universe? And the past boundary condition is just the usual wave function that we believe for the universe, which develop according to the many worlds into many branches in the future. And then you say that our universe has another boundary condition in the future which selects only one of these branches. That will be a solution to the measurement problem, and I would like to show to you how this is really consistent. It's not trivial. So I will use a toy model for the universe, and that will explain also the possible difficulties and how I solve it. So here is the thing I want to consider. Suppose we have a cavity with a large number of particles in it, say 10 to the 20, and I have two macroscopic possibilities. One of them, that all of them started in the left side, all the particles. Another macroscopic state is all of them started on the right side. And suppose that I have a superposition of these two macroscopic states, and I want to do a post-selection that will assure that we add only one of them. So what could be the difficulty about it? First difficulty is the following. Suppose before I consider this, I consider a very simple problem. I just have one particle with spin, and the time t1, I know that sigma x is equal to 1. So it's a superposition of sigma z equal to plus 1 and sigma z equal to minus 1. And I want to say that the future vector, by post-selection, post-selected sigma z equal to 1. If everything was a unitary evolution, there is no problem about it. But suppose in some intermediate time, I make another measurement and put a boundary condition that that measurement selects one of these possibilities. That means that this is not a unitary evolution anymore, and therefore it destroys the possibility of the future predicting what will happen in the past. I want to show that this problem does not exist when we have a macroscopic system. So the idea is the following. I am waiting a long time. If I wait a long time, after a long time, now the particles are spread everywhere. But there are still, by unitary evolution, two orthogonal states, one that evolves from all of them in the left side, and the other that evolves all of them in the right side. And I want to do a boundary condition in the future that selects one of these possibilities. And the question is now, what happens if I make some measurements in the middle? Will it destroy that possibility or not? And I will show why it does not destroy. But for this, I need one more information. You know that if you have a situation like this, say in classical physics, and you want to do time reversal that will make all of them go back to the left side. And you know that even if you destroy one particle, you move one particle to a different location, you propagate back in the past, and now it doesn't go to the corner anymore because there are many, many collisions, and going back to the corner is reducing the entropy, and therefore any change to an orthogonal state of even one particle later will make it impossible for them to go all to the left side. So it's going from the future to states where all of them are on the left side is going to reduce the entropy by a large amount, and therefore any disturbance will make this not possible. So the question is whether this is a problem for our post-selection. And the answer is not, for the following interesting reason. What measurement can I do on this system in the intermediate time? I can, for example, come and measure one particle and find it here. Now, this measurement is not the same as disturbing the particle to an orthogonal state, because the state that I found here is still an epsilon, small epsilon, to have the same state that I had before. Otherwise, I could not find it. So if I make a measurement like this, I see that there is an epsilon amplitude that I will still have the same state that I had before, and 1 minus epsilon that I have really a disturbance, an orthogonal state. So when I go back to the past and I do this measurement, there will be an epsilon amplitude that I will still find all of them in one half of the box, and 1 minus epsilon amplitude that they will all be spread in the box, because this was an orthogonal change. So therefore, the probability to find all of them on the left is proportional to epsilon squared, and the probability to find all of them in the other side, the right, in the left side, is 1 over 2 to the n, because now all the particles are spread, and therefore the probability to find that state is 1 over 2 to the n, and if n is 10 to the 20, this is absolutely 0. And I know, therefore, that my boundary condition in the future is safe. Even if I do a finite number of measurements, I will still get the fact that the boundary condition will postulate that macroscopic thing. So it's very interesting that people always thought that a measurement necessarily, because of the collapse, destroyed the possibility of time reversibility. But that's not the case when we have a macroscopic system. So this is the first part of my talk. And maybe I think it's better if I stop now and let you ask questions about that before I go to the next part, which I want to show that there will never be a super technology that will allow us to check if the manual is correct or not. But before I do that, I want to see if you have any questions about what I suggested here. Yes.
So I wanted to ask if epsilon might not be also 2 to the minus n, where n is the number of particles.
No, if you look, when you do any real measurement, you don't expect to find a probability of 10 to the minus, or 2 to the minus 20, because then you have to make 2 to the 20 experiment before you're successful. So when you do a real experiment, you're expected to find it with probability 1 over 100, 1 over, for example, if you make a measurement that looks at the particle in some region, the probability to find that is that volume divided by the total volume. So it's epsilon is of the order of 1 over million. It's not 1 over 2 to the 10 to the 40. Yes.
I'm not quite following. You said there's a chance, some epsilonic chance that you do this measurement and yet it's still in this, you haven't disturbed it, right? But if you do a measurement, then with 100% chance you've entangled that particle with the measuring apparatus, and now to time reverse it, I can't just time. If I do a measurement, then with 100% chance I've now entangled that particle with whatever measuring apparatus I used. And so I now have a much larger entangled state, and to time reverse it, I have to reverse. I can't just reverse.
Yeah, if you're looking at the real universe, not this toy model, then of course you can find the particle far away, right? Yeah. Okay. So what's the question?
The question is, you don't seem to have taken into account the extra entanglement with the measuring apparatus that would have to occur with 100% probability if you made an intermediate measurement. These particles will now be entangled with that device in a way.
Of course. So it's even better for me. I mean, I have now, say, an entanglement state where I have an ancilla that has one state where all the particles are on the right, another orthogonal state, or all of them are in the left, right? Now, when I do the post-selection, I post-select the unitary evolution of one of those, right? Then I go back in time and I ask, is it stable against some disturbances by other measurements, right? And I'm saying that any other measurement that I will do in the time in between will not disturb it because it will have an amplitude epsilon to still be that individual state. One, I had an entangled state, but the post-selection selects one of them. Select the external particle. Suppose I have the external particle spin up and all the particles are on the half side. And the spin down and all the particles are on the left side. And I want to do a post-selection that will select one of them. So the post-selection, when it comes back by unitary evolution, will select only that one which is spin up here and all of them in the right side, right? And the question is whether that post-selection survives if I do some measurements in the time in between. And I proved that it survives it. Okay? Any other questions? Okay, fine. So you all accept then that it's possible by two boundary conditions to make sure that we have only one result when we have, say, in a stellar experiment, I see a macroscopic spot in the photographic plate, it's spinning up, or another macroscopic spot if the spin is down. And I'm saying now that I can have a boundary condition in the future that when it comes back, it will select only one spot. And that will be a solution to the measurement problem that has the property, contrary to all other solutions, that I did not have to change anything in the dynamics. You see, all the ideas up to now to try and get one possibility in a measurement device, one event, was always to try and modify in some way the theory. Here I don't modify the theory, I only do two boundary conditions, but in between the theory remains the same as it was before. So it's a solution to the measurement problem without at all changing anything of the dynamics or anything of the theory. That is the thing that I like about the solution. So if there are no more questions, and you agree with me that I solved the measurement problem, I will go now to the other interesting question, and Lev likes to say the following. Yeah? What's that? Okay. Let's ask me what will happen if I have a super technology, and in this super technology, I will be able to check, for example, if I have one memory or I have another memory, I will be able to check that indeed I was in a superposition of these two, and therefore the many world will be proven to be right, because that is the prediction of quantum mechanics, that I am in this superposition. So I want to answer that by showing that actually there are some predictions of quantum mechanics that cannot be checked even by super technology. So here's the first example, which is very simple. I can prove that if I want to measure the momentum to given accuracy, I cannot do it instantaneously. It must take some finite time. Why? Because suppose initially I have a particle with a small uncertainty of position. Now I come to measure the momentum up to an uncertainty delta p, such that delta p is so small that delta x afterwards must be very large. Now, since the particle cannot move faster than light, there must be a finite time that this measurement will last. Otherwise, I will have a violation of causality. So here's an example. Suppose I start with a particle with a perfectly well-defined momentum. I now put on the particle with charge, electric field, that change the momentum, and immediately later I put the opposite electric field that brings the momentum back to the same value that it was before. So quantum mechanics predicts there was a time where the state was orthogonal, but there is absolutely no way to check it without violating causality. So this is somewhat a trivial example, but still an interesting example where there is a prediction of quantum mechanics that cannot be checked experimentally by any super technology. By the way, I want to tell you a very interesting historical story. When I was still a graduate student, but this result was part of my thesis, Bohm was invited, my advisor was invited to come to Copenhagen to meet with Bohm, and he took me along. So I came to the Bohr Institute, and I was walking in the corridor. I met Or Peterson, who was an assistant of Bohr. He asked me, what are you doing? What are you working on? I told him about this result. He said, you know, I think Bohr will be interested in it. I will arrange a meeting between you and Bohr. So here, there was this meeting in a small room, There was a blackboard, two chairs near the blackboard. I was sitting in one of them, Bohr was in the other, and the audience were Bohm and Peterson. Peterson. So after introduction, I asked Professor Bohr, I would like to tell you some difficulties I have about measurement theory, and I want to say connected with relativity. But he stopped me, and he said, no. Before you continue, I want to tell you something. He gave me a lecture that lasted 3/4 of an hour of things that I knew by heart about measurement theory. Then he said, that was a very interesting meeting. He got up and left the room. I was flabbergasted. It was unbelievable. I went out and Peterson ran after me and said, don't worry, you are in a very good company. A few years back, Feynman came and wanted to tell Bohr about his new approach using superposition of different orbits. And Bohr stopped him immediately, gave him a lecture for 3/4 of an hour why one should not consider in quantum mechanics orbits, and that was the end of this meeting, so I felt very happy about it. So, but now I'll give you another example where prediction of quantum mechanics cannot be tested that will be much more relevant for the question whether we can test the superposition of two different states of our brain. So here's the example. Suppose I look at the typical interference experiment of an electron. So I take an electron, move it this way or that way, and see an interference here if I have an ensemble. Now, there seems to be a possible problem with this. Because suppose if this is space and this is time. Suppose here I open a dipole for a short time and close it. That dipole will feel whether the electron is here or here, because the electric field, the dipole fields an interaction 1/r³ from the charge, and therefore it will feel a different interaction if the electron is here or here. So it can measure the position of the electron and therefore destroy the interference. But if we are in a relativistic theory, the electric field that I see comes from these locations, and the disturbance will go in the future light cone. So that measurement cannot disturb the particle and still can find out where it was. It looks a paradox. You know what the solution for this paradox? Everybody understand the paradox? I don't want to speak without being sure that you understand me. Yeah, okay. I will do it simple. Suppose there is an electron that stays here, or instead, this is the wave line. This is S, and this is T. So I have an electron that is at rest here, or at rest here, okay? And suppose now I want to make a measurement to find whether the electron is here or here. How do I do it? I have a dipole that I open for a short time and close and see what was the change of the momentum of the dipole. That depends on whether the electron is here or here, because the dipole feels a different force. Of course, the dipole must have an uncertainty in the position, so I can see its momentum. And therefore, if it was a non-relativistic problem, there would be no problem at all, because the dipole has an uncertainty position, and therefore it immediately puts a different potential here than here, and that introduces an uncertain phase. That's the usual thing. But in relativistic theory, the dipole measures the electric field that was produced at this time, and it will disturb the electron only at a later time. So there is time in between Well, I already found where the electron is, and I didn't disturb it yet. That is the problem. You understand the paradox? Because that means that for a while I still have a definite relative phase here, and I also knew the position, so I can complete here an interference and see that I have interference, even though I already have a knowledge of where the electron is. Is the paradox clear? Could anyone raise the hand that understood my paradox? Okay, good enough. So what's the answer to this paradox? The answer is the following. The electric field that is produced by electron in this region for the time concerned is much smaller than the uncertainty electric field in the vacuum. And therefore, I couldn't measure during this period of time whether the electron was here or here. The vacuum uncertainties, electron charge, electric field is much fluctuation, much bigger than the charge of than the field produced by the electron, and that's why we can do interference with the electron. But suppose now that instead of electron, I send here a molecule that has a very high charge. Molecule has many atoms, they are ionized, so now the charge is sufficiently big that the electric field here, due to that charge, will be bigger. The difference will be bigger than the quantum uncertainty of the vacuum. What helps us then? The answer is that the vacuum fluctuation here affects this very large charge enough that I could not do this interference experiment. So here is an example that if I have a large enough charge, I put it in superposition here and here, and try to do interference, there is no way that I could see it, because the vacuum fluctuation will make the phase uncertain enough that I could not have this interference. So here's an example of a prediction of quantum mechanics that cannot be checked. Of course, there is another way to explain it, and the other way is to say that any experiment that I do here will cause some radiation to go out. That radiation will be entangled with the charge if it's large enough, and that's why I don't see the interference. But if I look at the charge itself, I say the charge right now is in superposition of definite relative phase, and nevertheless I can't check it. And that thing is going to be relevant to discuss what happens in our brain. But first I want to make sure that you understand that. How many people understood what I explained here? Raise your hand. Not so good. Can someone ask me a question to make sure that you understand, because it's very important for the rest of my talk. Yeah. I have shown now that if you try to do a mass Zender experiment with sufficiently large charge, much more than 137, you could not do this experiment. No, you cannot do it if you do it in a short time. If you do it a very, very long time, even then, no, you can never do it, because the vacuum fluctuation is the same as, suppose I have a spin, a spin that has on it, in the z direction, magnetic field, random magnetic field that acts on the spin in the z direction. That random magnetic field will make the spin in the x direction precise with randomly, right? And therefore, there will be never a way to check the spin in the x direction if indeed that knocking is completely random. And it's exactly what happened with the vacuum fluctuation for sufficiently large enough charge. It makes the phase completely uncertain. That's because it all the time gets entanglement with the environment. Yes?
But the field, the electronic field is correlated or entangled.
Say it again?
Completely obvious that was forbidden. I mean, after all, you could always say.
No, but if you have a large charge sitting here, plus the superposition of this and that. Then you know that the electric field here will be a superposition. If it's here, you get one field. If it's here, we get another field. So if I make a measurement of the field here, it's like making a measurement of the position.
Right, but in this other example.
What?
I say in the other example.
No, but in the other example, you still have, you have to separate them, right? In order to, once you separate them at some given distance, then the field here will be different if it was moving here rather than here. And you see it by retarded. So actually, you can look here and see that it was here rather than here. There's no problem with that. And the only solution is the Macro fluctuation. Yes? Oh, sorry.
This is a kind of very general question, more general than what you just said. I'm trying to understand the argument, and my problem is, conceptually, it sounds like you're talking about classical electromagnetic theory, and then you talk about vacuum fluctuations, and you do this, and it sounds like you're telling a story where it's kind of classical electromagnetic theory in the face of some fluctuating medium, right? But people talk about vacuum fluctuations.
Yakir, can you talk into the microphone?
Can I just finish? People talk about...
It's well known that if you do a measurement in the vacuum of the electric field at a short time, you find that it's not zero, it fluctuates. It has uncertainty. Now, when you have a charged particle in a superposition here and here, the relative phase measures the electric integral of the electric field between there.
Conceptually, if I'm in a vacuum state and I believe the wave function is complete, it's not fluctuating.
Yeah, so I answered that.
The state isn't fluctuating.
No, okay. Oh, no. So I'm saying,
That the state,
I'm saying that
something really is fluctuating.
I'm saying that there are two different ways to think about it. In fact, we wrote an article. One way is to see the fluctuation. Another way is to look at the wave function of the whole universe and saying that when you have the particle here, you move the particle like this, it always has some acceleration, and therefore it has some radiation with many, many infrared photons and some photons that are not infrared, and the field outside is exactly that field produced by this radiation. So if you look at the wave function of the whole universe, it's a pure state. But if you try to isolate the charge, it's entangled with the field outside, and that's why you can't do the experiment on the charge itself if the charge is sufficiently big, because it gets entangled with the field outside. Different entanglement if it's here and here. So there are two different ways to look at it. Locally, if you look at the charge itself, or globally, if you look at the entanglement. It's two different ways to discuss the same thing. Any other questions? I want to, yeah.
Sorry, I share, Tim, some of your puzzlement, David. But you're saying these are two different ways of looking at the same thing.
Yeah.
Are they both happening?
Sorry?
Are they both happening? Is there both the vacuum?
I'm saying that there are two different ways to explain why. If you have sufficiently large charge, there is no way to make interference.
I understand the claim. I just want to know, are both things going on? Both the vacuum fluctuations, that will explain it, but also there's the photon emissions, that will explain it. Both things are going on, are they? Are both things going on?
No, there are two different ways of looking at the same thing.
Well, I don't really want ways of talking. I want...
No, you see, if you look at the global state, it could be an alien state of energy, right? And then nothing is changing. There is no vacuum fluctuation, nothing is changing, it's a stationary state. You have a charged particle in a given location, and you look at the ground state of the whole universe. So everything is stationary, the charge does not feel any fluctuation, but it's entangled with the field outside. So this is another one way to look at it. Another way to look at it is to look at the superposition here and here, still in the ground state. This will be entangled state. If the particle here, it's entangled, and if it's here, it's different state, but it's stationary. Everything is stationary. But you can look at it another way, locally, and explain why you don't see the interference. That's interesting that you can do it in the two different ways.
Got about 10 minutes left.
Okay, very quickly, why do I say that this is going to be relevant for the possibility of checking if our brain has one memory or another memory trying to do interference? It so happened that about a month and a half ago, there was a conference in Nazareth. The subject of the conference was free will. And during this conference, some people that do state-of-the-art experiments on the brain discuss a very interesting thing. They first of all said, you know, we have in the brain about more than 1 billion neurons and many more synapses. And they say that when they measure the activity of the neurons, it turns out that both if you are awake or you are asleep, the neurons are oscillating. They produce oscillating effects on the measuring device, and the effect is completely random. And also they show something interesting, that if, for example, they show the people that they made tests on, they show a number of pictures of famous people, say Obama, Stalin, etc. And they told the people that later they're going to ask them a question about that. And they found out that when they showed this picture, and the people try to remember them, there is a particular region in the brain where this memory was supposed to be stored, and then they show that the oscillation of the amplitude of the random oscillation of this group of neurons was bigger. And then when they showed them a particular picture and asked where was it in what order it was, there was suddenly a big spike in this fluctuation when they remember it. So the picture that I have is that I think about these neurons as many spin half particles, and the memory is stored in the z direction of the spin, and the fluctuations are in the x direction. So the brain all the time tries to stabilize that memory by sending all the time magnetic field, like magnetic field in the z direction. That's why when they pay attention more to this region, the fluctuations are bigger, because it's like an uncertain magnetic field in the z direction that causes the spin in the x direction to oscillate faster. So I then believe that just like we showed here, that when you have enough fluctuation, there is no way to check the different states, because to check the relevant state of superposition of states of one spin and another spin, you have to do it with the x direction. And this spin in the x direction fluctuates so much that it will be the same impossibility as the thing that I have done here. And they claim that if you try to stop this fluctuation, the only way to do it is to kill the person. The person, as long as he's alive, must have this fluctuation, this random fluctuation. So I believe that there is enough indication that, just as I said that when you have a large enough charge, you can't superpose it, that I think that our brain is an example of this kind. Thank you.
still have plenty of time for questions. Yeah. Yakir, why don't you go to the microphone over there?
Thank you. Suppose I do these charge interference experiments.
Sorry?
Suppose I do these charge interference experiments, but I do them in finite temperature. So I've got, I've got it effectively in a plasma, and so I've got a damping of the electric field. Will the effect still happen, or?
You're talking about the brain or about that experiment?
At the moment, just this experiment.
Yes, yeah, so what's the question?
If I'm doing it at finite temperature, so I've got a kind of an effective photon mass, and so
No, the Raman solution has nothing to do with temperature. Those experiments are done at 0 temperature.
Right, but I'm saying I'm asking about the alternative situation.
Sorry?
I'm asking about if it was at finite temperature, so I had an effective photon mass.
Yeah, if you do things at finite temperature, you may have other reasons why the phase will become uncertain. But the interesting thing, what happens if you do it in 0 temperature? You still can't do the experiment.
So I guess I'm asking because I'm interested whether this is relying on the long-range nature of the electromagnetic field, or whether if I have a mass term for the photon.
I have difficulty to understand the question. Can somebody? Yeah. If what? My hearing is not so good. Come here.
No, I got it. You hear?
Yeah.
He says, what if the field is massive and not a massless field, like a Yukawa potential?
Oh. No, but even, okay, so in that case, I don't have an argument why, unless the mass is sufficiently large, that the gravitational field will be different. Even a particle has Yukawa potential, it has also a mass. And you can prove the same thing, that if the mass is sufficiently large, and you try to do the experiment, the gravitational field will be different, and all the panels say this also, that if you have sufficiently large mass, you can't do the interference because the gravitational field will be sufficiently different. There will be entanglement.
Yes, that's right.
No, but I'm saying that we have no example like this. No, but because every particle has mass. So there is always 1 over R's potential, always. And therefore there will always be some example of this kind.
Yeah, I think that answered the question. Thank you.
Yeah.
So I'll take the liberty of a chairman to ask a topical question.
Yes.
This is about the many worlds. So let's just take the two branching worlds. And so the many worlders would say, let's say go back to your Stern-Gerlach. They would say if you have a spot here versus a spot there, each of the spots is 2 different worlds, but you say, no, I'm putting this future boundary condition in where I either select one spot or the other.
Yeah.
So maybe many worlders could say, isn't that cheating? Isn't that smuggling in one world by this additional post-selection? So what justifies the introduction of the second boundary condition? Maybe if I could speak for a many worlder audience.
No, but even in the many world, you see the advantage of, even in the many world, you see the advantage of, in a particular world, being pre- and post-selection and see all the nice new things about weak values, etc. That is true. So the fact that 2 boundary conditions are interesting is true also for the many world people. The only difference is that the many world people say that we see this in our world, and there will be other worlds where other things will be seen, and I'm saying that that's the only world that exists. But both of us will agree that 2 boundary conditions are interesting, because now there is a huge experiment that has shown the value of discussing this possibility of 2 vectors, because this opens the whole way for weak values and quantum walks and super oscillations. This opens completely many new fields, the idea of having 2 vectors instead of 1.
just make this question a little more precise. You have pre-selection in this superposition, and you have post-selection in
I
this.
don't have
No, you have boundary
no,
condition.
no, boundary. Don't call it, post-selection is done by me.
Yes.
Now I have a universe. A universe has two boundary conditions. Yeah.
Yes.
Okay.
So, can you allow universe to have the future boundary condition equivalent to our preparation? So we prepare superposition of two words, or split them. We split the two words, and we test it in a boundary that there are two words.
Yeah, but
The question is if
yeah.
one answer maybe it's impossible, another answer if it's possible, will you say that in this universe when the boundary condition post-select this two-word boundary condition, we really have a two-word universe? Or how you will?
No, I'm just saying that we have one universe, and I'm saying that in this one universe, we have just one word. That's it, very simple, and that's all we have. Why should I consider other possibilities? I'm saying we have just one universe and one world. That's all. Why should we have infinite number of possibilities that we can never check, and we can get all the predictions, but just doing that thing. So it's so much simpler. That's all.
Okay, unfortunately, we're out of time, so let's thank Yakir again for the nice talk.